Okay, coming to the slides. For SU2 only one row with 2s boxes are allowed, Young diagram. From dimension formula you can show that this one is 2s plus 1. Incidentally, the 2s could be an integer, even integer or odd integer. S is not giving you the j or s could be half odd integers also. So, 2s could be not necessarily even integer. It is even number of boxes for s being half odd integer, 2s can give you an odd number. Come back to your familiar notation. If you take a tensor product of spin 1 with spin 3 by 2, you all know this, even in the middle of the sleep if I wake you up, you know how to compose spin 1 with spin 3 by 2. You will start saying j1 minus j2 mod and go on, right. That is what I have written it on the right hand side. J1 minus J2 mod, which is half, in steps of 1 goes up to 5 by 2. So, now I am putting it in this notation so that you can map to your tensor product, direct sum. Right hand side is irrep, left hand side is a reducible rep. What are the dimensions? Spin 1 is dimension is 3, spin 3 by 2 dimension is 4, 3 into 4 is 12 and it has to split up into so many irreps so that the dimensions adds up to 12. Is it happening? For a spin 1 you will put 2 box diagram, for spin 3 by 2 you will put a 3 box diagram, because number of box plus 1 is the dimension, 2 plus 1 is the dimension, 3 plus 1 is the dimension. Now you combine and write the diagram. When you start combining it, something more you have to remember. Even here I forgot to mention that if you are looking at SU3, something probably I said in the earlier lecture, but let me assert it now. We did this, no? I wrote this. Okay. This is in general true as a diagram. If I say that I want to look at SU3, there are only 3 basic objects with which you can play around. If you put U here, D here and an S here, this box you are forced to put one of the 3. This is not allowed of SU3, but it is allowed for SU4. If you allow 4 fundamental objects. Okay. Up spin, down spin was for SU2, SU3 up quark, down quark, S quark, SU4 will be up quark, down quark, S quark and a charm quark and so on. If you had 4 objects, totally antisymmetric with 4 objects is possible. With 3 objects, making a totally antisymmetric of 4 objects is impossible. Okay. So, this diagram will not be there for SU3. What about this? UDS is forced here and this is just one dimensional. This I explained it, that any object with vertical column of n boxes is like as if it is a trivial representation added to things. Okay. So, I can add any number of them with a trivial unit representation. So, I can call that as AN with, I do not know, let me call it by our conventional one. This is like your trivial unit representation. It does no harm because it is like a identity state. Anything you multiply with it, nothing happens. So, this one also I can remove out and write this as, so this is like the A1 which I can ignore and write this as if it is this. These are the 2 possibilities for SU3. What is the dimension of this? This is 3 and 3, which is 9. What about this? This is probably 6 and this is 3. Okay. You can work it out and see what is the dimension. 3, 4, 2, 3 and then a hoop number. Okay. So, this is something which you have to remember, that whenever you have a vertical 3 box for SU3 you can ignore it. Whenever you have a vertical 2 box for SU2 you can ignore it. right. This is trivial for SU2. This is trivial for SU3. Okay. Clear? So, that is what I have done on the screen, that I have removed those trivial representations and written in the Young diagram. Going back to the screen, you see that spin 1 is 2 box, spin 3 by 2 is 3 box. You take the product keeping track of things. Whenever I have a vertical 2 box, I can ignore. Vertical 3 box is not allowed, okay, for SU2, doing it for SU2. So, these are the 3 diagrams allowed for SU2, and which one is spin 5 by 2 in this diagram? The one which has 5 boxes corresponds to the spin 5 by 2 representation. The one with 3 boxes, after removing the trivial representation, 2 box became trivial. Here you can make 4 box trivial and remove it out, and you get this. Is this clear? Okay, so this is the tensor product decomposition. Okay, it is very beautiful in the context of SUN, that this you rigorously, I am sure you would have rigorously proved in your quantum mechanics course, but here I am diagrammatically showing that every diagram is an irrep. For the SU2, the diagrams can have only a single row with so many number of boxes, each one is an irrep, but you can compose 2 irreps and they can undergo a decomposition into irreducible representation in a systematic way. Clear? Okay. The next question is about observables. Remember, when we did the selection rules, I said that every irrep is not only applicable to the states or the basis states, primary basis, binary basis or tertiary basis, but you can also apply to electric dipole moment vector, magnetic dipole moment vector, quadrupole moment vector and so on. So, those are the observables, and our aim is to understand selection rules even in the context of the continuous group symmetries, and that is given by your Wigner-Eckart theorem, which is not very different from what you saw in your discrete groups. The product of all the 3 states should allow for you a trivial representation. You have all done this, right? We did this. What is the trivial representation? It should allow me something which gives me this representation for SU2. If it gives me that, then I know that such a transition from an initial state to a final state triggered by an operator associated with an observable is allowed, otherwise it is forbidden. And I am going to assume that the system is respecting such a SU2 symmetry. If the system is not respecting that symmetry, there is no point in talking about it. If the system has a rotational symmetry, the rotational symmetry of spin particles is incorporated in the SU2 group. For such a group, I want to look at whether certain matrix elements are 0 or non-zero. I will not be able to say what is the value, but I can at least say that these matrix elements will be 0 or non-zero, and that is Wigner-Eckart theorem. I am sure you have all seen Wigner-Eckart theorem in your quantum mechanics course. I am just rewriting it in the group theory language. Okay. So, associated with the states Jm in the context of SU2, you will have observables which I am going to write it as OKQ, which is similar to writing a basis state like K comma Q. So, remember your electric dipole moment will be like a vector, and if this one is spin j is 1, then the 3 components of that vector should be related to the 3 components of that vector, which is what I have shown you here as an example. There is a slight modification writing it similar to your spherical harmonics, which you might have seen, that you rewrite things so that they are like complex conjugates of each other. The z component is like j is 1, spin 1, but the magnetic quantum number 0 is associated with the z component of the vector. The other components Ax and Ay, you take a linear combination of Ax plus or minus Iay. This is not new to you. You write e to the Im phi times cos theta PLMs, right. So, this is why it is called sometimes as a spherical tensors. So, if you just write Cartesian tensors, I should have written it as Ax, Ay and Az. To match with the states, you convert them into spherical tensors. So, if you compose 2 rank 1 spherical tensors, rank 1 means the first k value is 1, okay. Take 2 vectors, that is what I was saying, take a tensor product of 2 vectors in this notation, then you will end up getting, what are the possibilities? This one has j equal to 1, this one has j equal to 1, 1 cross 1 will give you 2, spin 1 and spin 0, and associated with that you will also have spherical tensor. So, this is exactly similar to my previous slide. If I replace this 3 horizontal box by only 2 box. So, whatever is applicable to the states is applicable to the observables also. This double box diagram is for a vector which you are all familiar. Electric dipole moment is a vector. You can start doing the compositions of 2 vectors and you can find what are the irreps. There you use this great orthogonality theorem to write the decomposition. Here I am not doing that. Okay. The next question is, can I find those explicit states from those fundamental objects, which is what you did also. If you remember, I took A1, B1, A2, B2, I composed them, and then I said that the one which corresponds to a trivial representation is A1 B1 plus A2 B2, that is the dot product, and we derived that using a projector. You wrote a projector and then you applied the projector on an arbitrary reducible representation and you found what you get, and then you wrote the corresponding binary basis, right. Similarly, you will have, if you compose 2 fundamental objects, if you take these 2 as one of those fundamental objects, when you compose it, what combinations of it will decide the state for this? That is not clear here. For that you need a projector, and that projector is nothing but your Clebsch-Gordon coefficient. Formally, if you see here, you have a tensor product of the basis states. So, this right hand side is a reducible representation. The projector is your Clebsch-Gordon matrix. Projector onto this will give you a particular state which belongs to an irrep given by exactly like what you did. So, this is, you can call the state which you write here in terms of this as a, these are fundamental bases, primary basis. You compose the 2 primary bases and get a binary basis. To get the binary basis, usually you will take a projector. Now, the projector role is played by the Clebsch-Gordon matrix. Okay. Similarly, you can show the generators, which was j plus j minus and jz, will now for this combined state obtained from composition of 2 primary states will involve j cross identity plus identity cross j. That should operate on, you do this mechanically, but this is the way the derivation will. Okay. Similarly, the observables, there is always a rhythm between the observables and the states. So, whenever you have an observable, you have to look at the commutator bracket with the generators, and they have the similar properties. It is like an eigenstate of Jz with j plus j minus, they increase or decrease by plus or minus 1. Now comes this matrix set. Earlier we did electric dipole moment, we took an initial state which is in one of the irreps of a discrete group, and we took a final state which is another irrep of the same discrete group symmetry, and then we asked the question whether that matrix element is 0 or non-zero. Now in this case SU2 symmetry tells you that the states have to be JIMI, other quantum numbers I put it as alpha, we do not need to worry about it. Similarly, the final state is JFMF. The question is whether such an observable, the operator associated with it, will it be non-zero or 0, and I am not going to give you the proof, there is a rigorous proof of showing it. What I want to stress on this is that to get a unit representation out of it, this will be proportional to the Clebsch-Gordon coefficient. What is the Clebsch-Gordon coefficient? You compose KQ multiplied with tensor product with JIMI, that is what is this composition, and you have to get the final state. You all know the properties of the Clebsch-Gordon coefficient. When will it be 0? If MF is not equal to MI plus Q, it is going to be 0. And similarly, JI composition with K has to have a JF, otherwise it is 0. So you can trivially rule out which matrix element is 0, which matrix element is not. Okay. There is a rigorous proof to show this. We cannot determine this element. This element is called reduced matrix element. Okay. I cannot find the number, but I can definitely say whether this matrix element is 0 or non-zero by looking at the Clebsch-Gordon coefficient, and that is purely from SU2 symmetry. Okay. So that is the selection rule for your. Suppose an experimentalist comes back to me and says that the quadrupole moment tensor, he can give me the matrix element for the 2 0 component, suppose. If he gives me this component K, then I know the CG coefficients, I can determine this matrix element for the quadrupole moment tensor with -2 for the Q. That Wigner-Eckart theorem is the selection rule in the context of SU2 symmetry, and in particle physics many processes, decay processes, you can rule out such a decay is impossible. You can tell from using just the SU2 symmetry. The SU2 symmetry is what we call it as an isospin symmetry in particle physics. Incidentally, you can use the isospins of few particles and look at a process like this where the operator, which is the S matrix, is like spin 0. So you need to see whether the isospin initial state and the final state are allowed. So here it is a combination of isospin of proton and a pion, and these can be worked out using your Wigner-Eckart theorem in the context of particle physics, and this is a very strong indication. Experimentalists do see that such a decay process, if it is the decay ratio between these two is 2:1. This has been seen, and we can account from purely from our group theory argument.